Maybe we should start.
Okay.
Let me press recording. Okay. Welcome everyone. Welcome to Harvard CMSA Quantum Matter in Math and Physics seminar series. We are very happy to have Liang Kong. He's actually around also in the North England, sorry, the New England area. So perhaps he will visit Harvard at some point. And today he will be speaking on his works on topological Wick rotation and holography duality. And I would like to remind the audience, please feel free to interact, ask questions during the talk. Please really feel free. And we just directly welcome Liang. It's all yours.
Yes.
Thank you very much. Thank you.
Yes. Thank Juven for kind invitation to this seminar. Yeah. So I will start my talk, but before I started, let me first turn off my video just in case the internet, because my internet is a little unstable. So just in case, I will turn it up when I answer questions. All right. Okay. So yeah, thank Juven again for an introduction. So this talk is a summary of many early work joined with my collaborator Hao Zheng and with other collaborators Tianlan, Xiaogang Wen, Zhihao Zhang, and Hao Zheng. Another source of this talk is an expository work joined with Hao Zheng with the same title, which is still in preparation. All right. Oh, how come it doesn't work? Okay, so I will start with a quick comment, remind people about the ADS-CFT dictionary. So one of the most important example of holographic duality is ADS-CFT duality. We record two important features of the so-called ADS-CFT dictionary. The first one is the gauge symmetry of the ADS set are mapped to the global symmetry on the CFT side. The second one is the ADS-CFT dictionary, especially for the correlation functions, is only defined when the boundary condition of the one-dimensional higher series ADS set is specified. Okay, this is an important feature. The reason I record this is because the holographic duality we discussed today share the same two property as ADS-CFT dictionary. Okay, well, although the relation is a mystery. Okay, so today we're going to discuss a new type of holographic duality based on the idea of topological Wick rotations. Let me set a convention. All the dimension nd in this talk is a space-time dimension. Okay, so this duality says that an n+1d topological order with a gapped boundary. I'm trying to highlight. I hope you can see it. Okay, an n+1d topological order with a gapped boundary is a holographic due to an one-dimensional lower quantum liquid. By quantum liquid, I mean it can be gapped, which include SPT order, symmetry protected topological order, and symmetry enriched topological order, also called SET. And SSB refer to spontaneous symmetry breaking order. And moreover, it can also be gapless. Okay. In today's talk, the quantum liquid can have a symmetry, but we restrict to internal symmetry of a finite type. And why is it called the topological Wick transition? Okay, it's showing this picture. This direction is the nth spatial direction. It has a boundary. Okay, it's a topological order with a boundary. The S refer to the category of topological defect on the boundary, and Z1S refer to the category of topological defect in the bulk. Okay, by a theorem of Kong Wen-Zheng, it says that this category have to be the Drinfeld center of the of S. Naturally, the defect in the bulk acts on the defect on the boundary. By just pushing the defect in the bulk to the boundary, they fuse with the boundary defect. Okay. On the other side, you also have S. Okay. And you also have ZS. There are two categories I'm going to explain later. But what happened? What happened? This rotation is fictional. Okay, it's not the real, but it's a kind of a bookkeeping device. It's like rotating the n spatial direction to the time direction, and this combining this data, this pair of data now combine together to form an enriched category. So let me briefly explain what are they. So S is again a category of topological defect in the quantum liquid. Okay, but sometimes, for example, in 1+1D case, a topological defect is simply a particle or topological defect line or particles. Okay, it's well known the particle can be understood as topological particle can be understood as the superselection sector of states. Okay, so you can also call it the superselection of state. Okay, the other one, Z1S, is the category of topological sector of operators. Okay, this will be clarified later. Okay, and roughly speaking, it is just a space of a non-local operator invariant under the local operator algebras. Okay, again, operator acts on state, so the topological sector of operator acts on the topological sector of the state. Okay, so you also have an action, and this action leads to an enriched category. Okay, yeah, that's the basic duality I'm going to explain. Okay, so the structure of this talk is that I'm going to start with explaining the holographic duality of the 2D, 3D topological order with a gap boundary with the 2D rational CFT. Then I move on the 3D toric code model with two gap boundaries, and its holographic dual is two gap faces in the 2D Ising chain. Then we generalized the Z2 gauge symmetry to a finite gauge series with gap boundaries, and correspondingly, on this side is a 2D gap the quantum liquids. Okay, now including SPD phase and spontaneous symmetry breaking phase. Then we move on to ND gauge theory. In this case, one can easily see that the gauge symmetry is mapped to global symmetry on the other side. Okay, and last we will talk about the general one, which means n+1D topological order with a gap the boundary. The other side is I already explained it, is a ND quantum liquid. If we have time, we will discuss further generations. Okay, let's start from the first one. So it's a 3D, 2D duality through the theory of a gapless age of 2+1D topological orders. So basically, I'm going to tell you about the mathematical theory of a gapless age of 2+1D topological orders. Okay, and from which we will derive this holographic duality. So consider a 2+1D topological order. Okay, it's described by a pair where C is a modulus sensor category, and small c is a chiral central charge. Okay, and now consider a gapped or gapless age of this topological order. It is consider it's a 2D worksheet. Okay, and what can happen on the 2D worksheet? The most general macroscopic observable on this 1+1D worksheet of the age is depicted in this picture. It has a lot of topological defect lines, and between two defect lines there are defect junctions. Okay, and the defect line can be fused horizontally. So this is the most general picture for all possible observable on the 2D worksheet. Okay, so it turned out that all these observables form and enrich the fusion category. I'm going to explain the data. Okay, so first it contains the label of the topological defect. So they're ABCs. Okay, leaving in the labeling set S. They're labels of TDLs. And another data is MAB. What is MAB? It is a space of field living on the 0D defect junctions. Okay, it's portrayed here. Okay, it's living in the as a 0D domain wall between two topological defect line. Well, in particular, it means that the space of field living on the TDL labeled by A is just MAA. Okay, because MAA can be viewed as fields living between two TDL with the same label. Okay, so MAA is a special case of MAB. Defect. So the field living on the TDL can be fused according to the OPE. Okay, but most general OPE is you can fuse the defect field in MBC with defect field in MAB to become a defect field in MAC. That's the more general OPE you can construct from this data. Okay, so these defect field, if you look at this data, it defines some kind of composition map. Okay, so what I'm saying is that if you're familiar with the category theory, MAB, this two index labeled space MAB, together with this composition map form a structure very similar to that of a category. Remember that what's the structure of category? Category just consists of a bunch of object, okay, family of object, and so it's just a label here. And for each pair of object, there is a Hom space. Same here, okay. For each pair of object or each pair of label, there is a space called MAB. Okay, so it's already a categorical data. So we will show in the next page that MAB can be realized as the object in the abstract category B. Moreover, this composition map can be realized the morphism in this category B. As a consequence, we obtain an enriched fusion category. B enriched the fusion category. Okay, I'm going to explain that. Okay. What happened now is that there is a trivial label in S. We should label the trivial topological defect line. Well, what does mean is trivial? Trivial just means the field living in M11 cannot be distinguished with the field living in its neighborhood. Okay, so that's mean the TDL is trivial. As a consequence, the field in M11 can live in the two-dimensional space, can live in the two cell. Okay, that's was the meaning of that. Okay, and subspace or subalgebra of field in M11 generated by energy momentum tensor. Okay, I assume it's it could be chiral or anti-chiral. But let me just use two labels to represent both cases. So the subalgebra generated by energy momentum tensor in this M11 turned out to be completely transparent on the entire 2D worksheet. This is just a definition of a conformal invariant topological defect. Okay, conformal invariant defect. Okay, or conformal defect. Topological defect is even should satisfy more conditions, right? More conditions than conformal, and the condition will pop up right away. So therefore, without loss of generality, we can assume there is a subalgebra in M11. Okay, it is bigger than the minimal algebra, and could be smaller than the maximal algebra. Okay, somewhere in between, or it can be both. Okay, in principle, can be both. We assume that it is transparent on the entire worksheet. Okay, since they're transparent on the entire worksheet, they can be viewed as symmetry in some sense. Okay, now we make a technical assumption. Okay, we assume V is rational in the sense that because this is the algebra, you can talk about the category of a module over V. We assume that it is a module sensor category. Okay. The reason we can do this is because when the H is chiral, V is called chiral symmetry. Okay. And is mathematically defined by a vertex operator algebra, or abbreviated as a VOA. Okay. If V is a non-chiral symmetry, the H is non-chiral. It is defined mathematically by a so-called full field algebra, which is nothing but a non-chiral analog of a VOA. Okay. So in both cases, you can talk about the mod V. Okay. In both cases, the mod V is a module sensor category. It makes sense as a condition. All right. Since V is transparent on the entire 1+1D worksheet, this MAB is clearly a V module. Okay, or sometimes we write it MAB belong to mod V. What is mod V? Mod V is to denote the category of V modules. Okay, now I want to emphasize that a V module in this case, it means that it has a module action, V action on it, right? V module have a V action on it clearly, but V module action is two-dimensional in this case. What does this mean? Because V is completely transparent, so V can act on MAB from left, from right, from top, and from bottom, without making any difference. Okay, so you can act from left, or you rotate around MAB by 10 times. Okay, then act. That will not make any difference. Okay, that's what I mean by MAB is a V module which support a two-dimensional V action. But that's precisely how the action of a V module over a vertex operator algebra is defined. Okay. Secondly, this composition map is clearly a morphism in mod V. The reason is that because V is completely transparent, when you fuse two defect, this action are compatible with the action of V. You can first act V on one of them or both of them, then do the fusion of two defect junctions. Or you can do the fusion of defect junction first, then have Vx on the final result. That makes no difference at all. Okay, so this can be translated into mathematics. The statement simply says that the composition map is a morphism in mod V. Okay, since we already proved that MAB is object in the mod V, and the composition is also a morphism of a mod V. By definition, okay, we obtain mod V enriched fusion category. Okay, where this fusion category, the Helm space in the fusion category is precisely just MAB. Okay, the space of defect field living on the junction. Why is a fusion? Oops. Why is a fusion? Because the defect line, okay, can be fused horizontally. You can see it clearly from the picture. Right? MAA, the defect line labeled by A, can fuse with defect labeled by P. Okay. All right. Okay, so now it's convenient to introduce abstract module sensor category B and identify it with mod V by a braided equivalence. Okay, why we want to do that? You can just say, well, it's already enriched in mod V. Why bother to introduce another one? I think it's just convenient. You will see why we do that in maybe in the next few slides. But the point is, I didn't tell you the precise relation between mod V and S. In principle, you can twist this enrichment by a braided automorphism. Okay, that means even you set B equal to mod V, well, you can still twist the enrichment by braided autoequivalence. This is the important data we need. Okay, so that's why we introduce the abstract category B. It turned out all the correlation function and the OPE among defect field can be recovered by the triple. So this triple is enough to recover everything. Every possible correlation function on the defect lines, OPE between defect junctions, okay, or in any OPE in any defect, or OPE in the bulk, okay, bulk just encoded in M11. Okay.
Excuse me.
Yes.
Not sure. Maybe one page earlier, just one slide back. The assumption there. So you say the TZZ bar. Is that the expectation value for what? For energy momentum?
It's not expectation value. It's just algebra generated by energy moment tensor.
Oh, okay.
Yeah.
And so I just want to understand what's this.
Oh, it's include the prime field of the energy moment tensor and all its conformal descendant.
Okay, and this is a subset of
yeah. For example, in this case, in the chiral case, this is simply generate sub VOA.
Okay.
In a non-chiral case, it will generate a sub full field algebra.
And your assumption is V is
rational.
Okay. Yeah. V. So which exactly is the assumption for this statement? Like which part is assume V is rational?
Yeah. So this is a non-assumption because in general we say that the minimal requirement is this to be transparent, and the maximal you can have is the whole M11 is transparent. That's the maximal choice. But I just say V is somewhere in between. So there's no assumption there. The assumption is we assume V is rational and the model V is a multi-tensor category.
Okay, but even if V is not rational, V is still in between M11 and T.
Yes. This technical assumption is simply because we only know how to do this. Irrational case, we don't know how to do because the representation theory is very complicated. It's, mathematically have not been developed, fully developed.
Thanks. Thank you.
Thank you.
Can I ask?
Yeah.
So you say that you have T and everything generated by T. So that means descendants of T, but T itself is not a primary, right? So.
Yeah.
Okay. Okay, yeah. So it's still like T itself is a descendant of the identity, right?
Yes, it's a descendant of a vacuum. Okay. Yeah, but I assume that so vacuum is in it in this subalgebra, and the T is in it. All the conformal descendant of this is in it. Yeah, you're right.
Okay, thank you.
Thank you for the correction. Yeah. All right, so last we said it's turned out that all this correlation function and OPE can be recovered from this triple. Is pretty powerful categorical way of packaging all the informations. Okay, all the data on the categorical side is packaged in this MAA or MAB. Okay, and using this phi and VOA, you can repackaging. You can recover everything. Okay, it's a non-trivial statement. So let me summarize. So the gapless boundary of 2D, 2 plus 1D topological order can be completely characterized or classified by the triples, okay? Where V is called chiral or non-chiral symmetries. For a chiral gapless boundary, V is a rational VOA, okay, of central charge C. For a non-chiral symmetry boundary, V is a rational full field algebra with a chiral central charge C, okay? And when V is trivial, simply a complex number can be viewed as a trivial VOA. It describes a gapped boundary. Okay, so in this way, you can see a unification of the unification of the mathematical description of the gapped boundary and the gapless boundary. Okay, and another data is this braided equivalence. Okay, S turned out to be a fusion category. Before I talk about the next data, I want to point out to you that from all this data up to here, okay, it simply come from analyze of the observable on the worksheet, and without considering the bulk, except I claim the central chart, you see. But this data is not included so far. Okay, it will enter in this condition. So we require the fusion category to equivalence the braided equivalence. Okay, this data it determine the enriched category BS, where so-called canonical construction. I'm not to give the detail. You just leave it as the black boards. Okay, but the important thing is this: this condition is enough to determine the relation between the bulk and the boundary. Okay, one of the manifestation of this is the following theorem. It says that the bulk is the center of the boundary. It means that more precisely, the dream field center of the enriched category associated to the boundary is precisely the modulus density category in the bulk. Remember that in the gapped boundary case, this is the well-known result. Okay, it says that in the gapped boundary you have a fusion category. Okay, enriched in category vector space actually, and its dream field center is the bulk. That's the bulk is center of boundary statement for the gapped boundary. But now we have a gapless boundary, have the same property. Okay. Yeah. All right. This theorem can be reinterpreted as a so-called topological Wick rotation. It says that the all gapped and gapless edge of the 2+1D topological order can be obtained by performing the following topological Wick rotation trick. Then adding the data of chiral and non-chiral symmetry by hands. What does this mean is that you can consider a domain wall, gap domain wall between two topological order. Okay, a 3D 2+1D topological order. One is CC, another is BC. Okay. Oh, that's a mistake. I copied it wrong. Copied from here. The B is this is not true. Sorry. B is not the dream field center of this. This is for the condition in the next pictures. So this is not true. Okay, you should ignore it. Okay. So B with this physical configuration, what you can do to produce a gapless edge of C is simply rotating this part to a vertical direction, pretending this fictional 2D topological order living in a time direction. Okay, this is just a bookkeeping device for to record the data of enriched category. Enriched category. Now you have to put in the data V and phi by hands. Okay. Yeah, the rotation only take care of the categorical part. All right. One of the special case of this is the bulk is trivial. When the bulk is trivial, you do this rotation, you simply obtain the holographic duality, because on this side is a 2D phase with a gapped boundary. And then now, if you after the rotation, it become anomaly-free 1+1D quantum liquid in the one dimension lower. Okay, I want to give you some examples. Okay, so in order to talk about this example, let me recall some basic things. The first is the Ising modulus density category. It can be viewed as a representation category of famous Ising VOA with a central charge C = 1/2. So this category, modulus density category, has those three simple objects and famous fusion rules. Okay, another modulus density category we need to consider is the dream field center of Ising. Is also called a double Ising. Okay, it's equivalent to the Liang tensor product of Ising and Ising bar. Ising bar is the same Ising, same category as Ising, except the braiding is chosen to be the anti-braiding of Ising. Okay, so that's called Ising bar, or you can call it time reversal of that. It has a 9 object. I will denote the object in the following way. Another modulus density category involved in our discussion is the famous toric modulus density category. It has 4 simple objects and with the fusion rules, famous fusion rules. Okay. All right. So now we want to consider 3 possible non-chiral symmetries. The first one is the P, which is tensor product of Ising VOA with its anti-chiral counterpart, which means it is the same VOA except all the field has anti-chiral variables Z bar. Okay, and it can be this viewed as is example of full field algebra, and it's precisely the tensor unit in the double Ising category. All right. If you don't familiar with the tensor category language, you can think about the partition function of the P. That might give you some familiar feeling. Okay. Q is the extension of P. Okay. Not only contain the P, it also contains an additional part, okay? And R is even bigger. It's contain Q and another part, okay? So so it turned out that the PQR are condensable algebras in this this category of double Ising, and the R is turned out to be a Lagrangian algebra. More precisely, because P is a full field algebra, you can talk about the mod P. Mod P, because P is just a tensor unit in this category of double Ising. So mod P is precisely the Ising, double Ising. Okay. If you don't understand this notation, you can just ignore it. It's about something related to condensation. I'm going to explain. So so we got a Brady isomorphism, a Brady equivalence between mod P and a double Ising. Okay. It can also understood as condensing P give the double Ising, but P is trivial in this category. So condensing is basically just doing nothing. However, if you condensing Q, it will get a non-trivial result. It's a famous result by condensing Q, you got a toric code. Okay, so then you also got a Brady equivalence between mod Q and the topological order. Another Brady equivalence we need is mod R and the category of VAC. Physically, it just means condensing R in this category, you got a trivial phase. Okay, trivial phase is described by the trivial modular sensor category, which is a category of finite dimensional vector space, just denote as a VAC. Okay, so now I want to emphasize that there are three Brady equivalents from mod P to their to three modular sensor categories. Okay, we need to remember this data.
Sorry.
Okay, now I want to describe the 4 anomaly-free 1+1D gapless quantum liquid defined by 4 triples. What I mean by anomaly-free. Anomaly-free simply means it's 2 plus 1D bulk. It's trivial. Yes.
Question. Yeah. Sorry, I something I didn't understand. When you do topological Wick rotation, things like you are distinguished time and space direction in some way.
Yeah.
But how is that coming in the category theory? Why the time and space matter?
Yeah. So at this stage, at that stage, the topological Wick rotation does not have a precise physical meaning, except it's a bookkeeping device so far. It does not have precise physical meaning. Maybe eventually in the future, we probably, and if we understand more, we could provide some physical meaning. It says something about the space and time for sure, but right now I was not able to answer this question. At this stage, I can only say that it is it's just a trick, and this trick turned out to be very useful. You will see. We're gonna use this trick in many different ways. It produced some interesting results by using this trick. For example, computing the fusion of gapless wall, gapless edges. This is a very powerful trick. Yeah. Right now, it's just a bookkeeping device.
So when you draw the picture or motivate in this,
yeah. So the motivation is this. So you see here, everything in the I draw this in the spatial dimension. When I put it in the vertically, I just want to emphasize that what I'm trying to emphasize is that this B is in some sense encode observable in the space-time, in the 1+1D space-time. That's what I'm trying to emphasize here. So the label for TDL, the label of TDL can be they just, you know, TDL it can only fuse in the one direction, right, horizontally. So that means they can be, if you view the vertical direction as a time direction, you can restrict TDL as a particle on the domain wall. Okay. But then there is a 2D worksheet, and this 2D worksheet have these structures and that relate to B, right? B is a mod V actually. So I want to encode these 1+1D worksheet data using this B and S. So so that's why we introduced this kind of weird rotations in the vertical. So have some fictional. So this thing can be viewed as a fictional 2D topological order in the vertical direction. Right now, it's just a bookkeeping device, and just tell you that okay, the data of observable in this vertical worksheet, 2D worksheet is an enriched category.
So the relation to rotation from the space to time, that physical picture is not clear from the category.
Not clear, exactly. Right now it's not clear.
There's some dimensional reduction type of understanding, however, from the category from 2 plus.
Yeah. Right now, so dimension reduction will come up in the later part of my talk. I think the part of this can be understood in the following way. The topological order, for topological order, the enrichment is trivial. You can view a topological order have something. What happened on the space-time direction of the topological order is somewhat trivial. Most of the data are restricted to the spatial dimension. You can view it in that way. So you can sort of ignore the time direction when restrict only the spatial dimension. Then in this way, you do a rotation. The spatial, the nth spatial dimension become time direction. That's the intuition I had in mind. Because, for example, when the face is gapped, for example, when B is trivial, you rotate. You got a fictional trivial face in the vertical direction, but that just means B is enriched. B is a category vector space. So a fusion category S enriched in the category vector space is nothing but it's S itself. Okay, that's the gap phase. The gap age. The gapped age, the enrichment is enriched in the category vector space, finite dimensional vector space. Okay, so this picture match.
Thanks.
Yeah, it's just tell you that in the gapless case, there is something non-trivial happening in the worksheet, as if there is a fictional new non-trivial topological order, 2 plus 1D topological order living in the vertical direction. Right now, that's the only interpretation I can give.
No problem. Thanks.
Yeah, beside the bookkeeping device.
All right. Another question: when you say that the bulk is the center of a boundary, that relation is independent from the input of the V,
right?
The
Exactly.
Additional data you find a boundary.
Right.
Another thing is the second one is this phi. Is the phi there has anything to do with the third definitions? The way you are define the bulk as a center of boundary, does that require the data of phi?
No. This simply follow from the last equation, from this condition.
Okay.
This condition simply say that the S can be physically realized the gapped boundary between topological order C and topological order B with the same central charge.
So why do we need phi? The second one.
Phi. The reason you need a phi. Well, it will be clear maybe in the later slides. But it just tell you that. Well, it's explained in this page. Essentially, you got enriched category enriched in mod V. However, there are different enrichment you can define by introduce braided equivalence between mod V and mod V, between itself. You can twist it by auto equivalence. So this data is important because right now I did not tell you how mod V acts on S. That's that this stage is not clear. You need additional data to define the enrichment. Yeah, this is the technical part. Maybe you can ignore at this stage, but it will become clear when some example come up.
Okay, thanks. Thank you.
Thank you.
Right. Can I also just,
Yeah.
sorry, one more question is, in this example with the Ising, it happens to be the case that the representation category of the Ising VOA is this thing you call IS,
Yeah.
but also that the collection of all topological defect lines that act on the Ising VOA is also that category. But those are not generically the same, right?
Yeah.
So
yeah.
Am I supposed to be thinking of this when I see IS in these slides? Am I supposed to be thinking of this as topological defect lines which act on a 2D VOA, or am I supposed to be thinking about it as representation category of the VOA? So
so I'm going to talk about it now, okay?
Oh,
so
okay.
in this 4 anomaly-free gapless quantum liquid, okay, the first example is given by a triple, and the P is the non-chiral symmetry, and the enriched category is given by this pair. In this case, the IS is the same Ising module sensor category, but in this case, you should understand it as the category of defect line. You should view this Ising as a fusion category, label the topological defect line.
I see. So if I had a holomorphic VOA, then in this case, for example, this would be non-trivial, even though rep of V would be trivial.
No, because if P is a holomorphic VOA, this have to be trivial.
Yes.
Then this Ising, this part have to be trivial because there is a condition. Because in this case, the C is trivial, right? Remember, we have a theorem. The theorem says that this enriched category, if you compute the dream field center of this enriched category, it should give you a bulk. But the bulk now is trivial, so the dream field center of this enriched category have to be trivial. If the dream field center of the Ising is trivial, then this Ising have to be trivial by that result. Okay. So you cannot have just a single Ising. So it means that it will pop up here. You will see what's going on.
Okay, yeah, maybe I'll just wait a bit.
Yeah, Thank you. So I think this will become clear when you see the next few examples. Maybe let me skip. Let me jump to the first one directly. So what happened is that if you if you demand a smaller non-chiral symmetry, then the topological defect line allowed, because topological defect line are required to make this non-chiral symmetry transparent on the entire worksheet, right? So topological defect line should respect this symmetry. So if you require a smaller non-chiral symmetry, the number of topological defect line is non-trivial. It has a lot. Okay, but if you increase non-chiral symmetry to the maximum R, it turned out that you don't have any available topological defect line anymore. Then everything is trivial. This is the case you were talking about. So because so if you choose non-chiral symmetry R, its mod category is trivial, is vague. In this case, the so-called underlying category of the enriched category is have to be vague, because altogether their dream field center is trivial. There's no choice. So this cannot be non-trivial anymore. If this is non-trivial, its dream field center will be the dream field center of whatever this is. Okay, and so but since we said it's anomaly free and the 2+1D bulk is trivial, okay, there's no much choice. And you can see a computation here. The non-chiral symmetry getting bigger, the number of topological defect line is decreased.
Okay. Yeah, I think my issue is that my confusion was about the fact that C equals to 0. Yeah. Yeah. Okay.
Yeah.
Sorry. Thank you.
So in all four cases, in all four cases, the space of non-chiral field leaving on the 2 cell, namely M11, are all R. Okay. But in the first 3 cases, the non-chiral symmetry are not equal to M11. Okay, they are not equal. Only in the last case, they coincide. Okay. All right, I'm behind my schedule. But any questions? I didn't say anything about the Q, but the Q is just sitting in the middle. But you can see, okay. So, but let me give a comment. So in this case, Ising have 3 object. So basically, you can view there is a 3 topological defect line. Okay, simple topological defect line. When the symmetry increased to Q, the topological defect line reduced to 2 because the category representation of Z2 representations only have 2 simple objects. Okay, this one also have 2 simple objects. Okay, when the symmetry increased to R, only the trivial topological defect line left. Okay, there are no more defect line allowed because symmetry is too large. All right. Yeah, so this also I think is a unique feature of our theory. It says that when people talk about people talk about double Ising CFTs, just a double Ising CFT. But in our description, there are at least four different triples. Okay, so our interpretation is 4 different gapless quantum liquids because the symmetry on the worksheet are different, and the topological defect line, the number of topological defect line are different. Okay, all right. So this is one example. Now I want to give you some other example. Now I want to give you some example of a gappable gapless edge of a 2+1D toric code. Okay, so the first triple you can have is the P is the same as is the tensor product of Ising VOA and its anti-chiral counterpart. Okay, and in this case, the enriched category is quite non-trivial. The enriched category S is defined as the fusion category of the right Q module in the Ising, double Ising. Okay, this is maybe too abstract. Let me make it more explicit. S have 6 simple objects. Okay, 4 of them can be identified with 4 anion in the bulk because the bulk is toric code. Okay, so you have this 4. And the other 2 can be identified with 2 twist defect in the bulk. So it has a 6 topological defect line. And the most important thing is that in all these cases I'm going to talk about, the enriched category, if you compute the dream field center, is always the bulk. The bulk C in this case is nothing but this 4 particles. Okay, it's toric code. Yeah, I really should write the TC here. TC represent the toric code modular sensor category. Okay, so another triple is sometimes called canonical gapless edge. Is you choose the non-chiral symmetry to be Q. Okay, because the mod Q is TC. Okay, because condensed Q in double Ising give you toric code. Okay, and it turned out that the labeling set for the topological defect also have to be toric code. Okay, another interesting one that's to show the flexibility of our theory is this one. So you choose the non-chiral symmetry R. In this case, mod R is vect. Okay, so you can only enrich in vect. Okay, but you can choose the bottom one to be the rep Z2 because the rep Z2 give you the dream field. Its dream field center is TC. Okay, it's a bulk. Okay. But in this case, what is interesting is that this triple is not primary. Okay, it can be factorized into 2 parts. The first part is this one. Okay, the non-chiral symmetry is trivial. A non-chiral symmetry is trivial simply means it's a gapped phase. It's simply corresponding to smooth gapped edge. Okay, the other part is the anomaly-free 2D gapless liquid we're talking about in previous page. Okay, it's just nothing but this. It's anomaly-free. So what does this mean? This means that this gapless edge is obtained by first have a smooth gapped edge, then you stack with 1+1D anomaly-free CFT or quantum liquid. Okay. Similarly, you can get another one. In this case, it's a stacking of a rough gapped boundary with another with the same anomaly-free 2D gaps liquid. Okay. Similarly, you can produce many more by doing multiplication of a smooth or rough gapped edge with any anomaly-free 2D gapless liquid. Okay, so I think this show this is the intuition physics had in mind, and this mathematical theory should catch these physical intuitions. Okay. All right, let me move on. So we can yes.
maybe you explain where is the smooth and rough?
Oh,
gap edge?
torical,
Just
yes.
torical, right? This
The smooth is the M particle condense boundary. The rough is the E particle condense boundary.
that I know, but this only apply to torical is a more general statement here.
Oh no, this is just torical. This is a gappable edge of torical. Just
Okay.
the bulk is torical. Yeah.
More general other.
Oh, you mean if this statement generalized? Yes, this statement generalized to all the cases. You can always have some gapped edge stacking with anomaly free 2D gapless liquid. Then you got a non-trivial gapless edge of certain box topological order. This statement is more general, but all the other these only work for torical.
But this statement probably will not be true for the 2 plus 1D bulk with EA quantum hole, the EA Chern-Simon gauge theory.
Oh yeah.
So
in that case, yeah, not include that case, I guess.
But
our theory covered that case in general, but not in this statement though. I mean, in this statement cannot generalize there because in that case there is no gap edge. But
right.
our theory covered that case. I mean, you just choose the EA VOA on the edge, right? With a central charge 8, C equal 8.
Okay.
Yeah.
So,
even though the topological skeleton is trivial in that case, but this is non-trivial because this data of a chiral symmetry is non-trivial.
So the general construction of the gapless edge sometimes may have the gapless theory also need to cancel something from the bulk. It's not quite an anomaly, but some generalized notion of anomaly, right? Because you are trying in the fifth, you have a tensor product between gap edge and anomaly free gapless theory, but in general, the gapless theory might also carry the carry some non-trivial. It's not anomaly. It's not total anomaly.
So far I only talk about the anomaly free. I didn't discuss that situation. Yeah.
Okay.
That situation you also have to take care of the bulk then. Yeah, I'm only talking about the anomaly-free quantum liquid so far. Won't affect the bulk. Yeah.
Okay.
Yeah.
Will there be case also the gapless 1 plus 1D gapless theory also carry some also try to cancel something from the bulk? Is my question clear?
No. It does not cancel anything on the bulk. In my setup, it's anomaly free. It won't affect the bulk.
But I say that
in your setup, maybe yes.
Okay.
Yeah,
No.
if you consider something a gap is liquid with some gravitational anomaly, then the situation is different.
But I say that EA quantum hole state is one example that you cannot really try to write this way, right?
You can I write in this way? Well, if you do that, you also have to take care of bulk. The bulk also changed. Yeah. Yeah, you cannot write in this way. Maybe I should say, yeah, you cannot write in this way anymore. So yeah, to generalize the last statement, you should be careful. Okay.
So I said that will you refine this statement to include those examples? Like
yeah, you can refine those, and you also have to take care of the bulk part.
I said, will you do that in your talk? Just want to make sure.
No, I won't.
All right.
Yeah, there's just some example for you to get some feeling. There are more examples. We can stay here forever, but I want to move on. Maybe.
I understand, but those examples are probably more interesting than the one you are discussing right now here, right?
Oh yeah, I probably agree, but torical is yeah, actually when I prepare the slides, I have given this talk in some other places. I give other example in the chiral gapless edge, but I feel torical is easier to understand. That's why I
Okay.
Yeah.
Okay. Thanks.
Yeah, you're welcome. Okay, so let's move on. So you can see that the data of the triple may play somewhat different role. Since this data, the enriched category encode all the topological and categorical data. We call this enriched category the topological skeleton of the H. And the other two data are called the local quantum symmetry because they're either VOA or full field algebra. They're both symmetry, chiral or non-chiral symmetries. In more general setup in the future, we could also replace it by conformal net of a local quantum algebras. Sometimes I would just abbreviate it as LOA, local operator algebra, because conformal field theory also have another equivalent formulation in terms of conformal net of a local operator algebra. Okay. It will pop up in the later slides. So know that the topological skeleton is an abstract enriched category. It's only require a precise physical meaning only after we identify B with mod A, where the using the Braided equivalence. Okay, before you do that, it does not have any physical meaning. It has a physical meaning in the topological way. Okay, so it suggests that a gap or gapless quantum liquid in general, not necessarily restrict to this this dimension, it can be more general direction, can be described by two types of data. One is I will denote it as local quantum symmetry. Okay, another is a topological skeleton. So in this particular case is this data is the first two pair, another is the enriched category. Okay. One justification of the statement is that the same topological skeleton can be realized by a gapped phase. Okay, there was some work about this. Now, but the point is, if you just give me a topological data, topological categorical data of the topological skeleton, that's what we call, it does not tell you whether the phase is gap or gapless. It can be gap or can be gapless. Depends on what local quantum symmetry you associate with it. If you associate with non-trivial VOA, well, it's gapless. If you associate with a complex number, a trivial one, or any orbifold of complex number, that's SPT, then you get still get the gap one. You're gonna see this in the later slides. Okay, so I want to mention that this holography has a long history. Start from Wheaton's Chen-Simon-Wheaton theory and the duality between this and 2D-ZW models, and also Morris Heiberg's work showing that the representation category of chiral algebra is given a modular tensor category, which was later shown to produce a Rastikin to our TQFT. Okay, so and there are a lot of related work, but the story I won't go through all of them. So the story told in this talk is unique, is that the topological Wick rotation and the enriched category are not used in other places. Okay, all right. So let's move on to the next example of Ising. So I want to talk about the toric code and Ising. Okay, Ising chain. Okay, and generalization to the finite gauge group. Okay. All right. So I'm really far behind. So let's see if okay, so maybe I could be brief here. So for Ising chain, this is a well-known Ising chain, and B and J are coupling constant, and S, Z are polymatrix. And this model have a global onside Z2 symmetries given by the multiplication of all Xi at all sites. Again, similar to the previous case, if you analyze this 1+1D worksheet of this Ising chain, you always get this kind of picture. Okay, so the microscopic observable in the 2D spacetime form an enriched fusion category, same as before. Okay, except in this case is that what is the TDL? Remember in the TDL, if you look at it from condensed matter point of view, or using the spatial dimension point of view, this is just a particle, and it is well known that particle can be understood as a super selection sector of state. Okay, so in this case, you analyze what are the super selection sector of state. It turned out there are two. Okay, one of them is, okay, so before I talk about it, I would denote the eigenstate of X be plus or minus. Okay, so the ground state is all plus at all site. Okay, the sector, the trivial sector of the super selection sector contain the ground state. It's a trivial sector. There's another sector contain a non-trivial state, which is plus everywhere except at one location. It's minus. Okay, these two sectors form a category which is called the category of Z2 representations. Well, for the symmetry broken phase, there are also two superselection sector of state. And using the eigenstate of Z denoted by spin up and spin down, you can write out this two sector. For the limit of time, let me skip this part. Okay, so in a gapped case, we also have to replace the chiral and non-chiral symmetry V by something else. Okay, so it's the mathematical replacement is a topological net we introduced in one of my work. It's a net of U-symmetric local operators. Okay, and turn out the mod V now becomes the category of sector of this net, and you can prove this category is given by the Drinfeld double of rep Z2, which is precisely the category of anion in the toric code. Okay, but this rigorous treatment perhaps is not very illuminating. So let me do an unrigorous treatment, maybe more intuitively clear. Roughly speaking, these sectors are they are sectors of U-symmetric non-local operators. What do I mean by that? Intuitively, it just means the space of unconfined non-local operators invariant under the action of a symmetric local operator. For example, in this case, you can have four sectors. One is trivial sector. It simply contains all the local operator, U-symmetric local operator. Okay, for example, the identity operator, or this one. This is U-symmetric because Zi plus 1. Okay, so it's a local and the U-symmetric. A non-trivial sector consists of denoted by M. It can be it consists of operators of infinite long strings from negative infinity to location I. You multiply all on every side xk, sorry. Okay, this produces a non-local operator, which is symmetric. Okay, it's non-trivial sector. Another one is E. This one contains an infinite long string operator by multiplying a symmetric local operator infinite number of times, and this this zk1 appeared twice, so they all canceled. As a consequence, you only produce the so this multiplication is essentially a zi at I point and the zi at infinity. Okay, so this is a non-trivial sector. Another non-trivial sector is multiply this two. You got F. Remember this 4 is precisely the 4 particle in the toric code. Okay. All right. So what is the MAB here? Remember MAB, the meaning of MAB, but in this case, it translated to the space of operators that map the sector A of state, or the TDL labeled by A, to the sector B of the state. Okay. So in particular, MAA is 1 plus M. Let me explain that. Well, M11 consists of the operator mapping a trivial sector to the trivial sector. Clearly, 1 is in it, right? Because identity operator or any local symmetric local operator does not change the sector. So this definitely in it. But M is also in it. Why? Because M acts on this vacuum. Look at the vacuum. Vacuum is precisely the eigenstate of M. So M acts on it, doing nothing. So leave it invariant. So M11 can consist of this two. Okay. Similarly, you can check the other 3. As a consequence, this also form an enriched fusion category. Okay, it's a rep Z2 enriched in the category of toric code. And the Helm space of the enriched category is precisely MAB. Okay, so we again obtain an enriched category. Let me summarize. We already showed that the symmetric phase of the Ising chain give you this enriched category. But the symmetry breaking phase give you another enriched category. Okay, I want to remind you that the toric code, this TC is the modular tensor category of particles in the bulk of toric code. Okay, precisely. And the rep Z2 is the category particle on the smooth boundary of the toric code. And the VAC Z2 is precisely the category particle on the rough boundary of the toric code. What does this mean? We're talking about 1 plus 1D Ising chain. Okay, so we obtained precisely a holographic dual of 2 plus 1D toric code with 2 gapped boundaries, and it's corresponding to 2 phases in the 1 plus 1D Ising model. Okay, this pair is mapped to an enriched category. Okay, that's another example of a holographic duality. This is pretty well known. Now you can generalize this to a finite group. So it's well known that 1 plus 1D bosonic or fermionic gapped quantum phases with a finite answer symmetry G, a finite group G, okay, are classified by a pair. H is a subgroup of G, and omega is a co-cycle, two co-cycle, okay? And it was obtained many years ago using a microscopic method. Start by analyzing a ground state wave function using local unitary transformations. Okay, it was later reproduced by Fritz Telemann using holographic duality. Okay, and we also obtained this result, but our argument is independent of we can have an independent argument. So we basically prove it using a macroscopic method. Okay, so let me state the macroscopic result. It says that the macroscopic observable in the 1 plus 1D bosonic fermionic gap phases with a finite answer symmetry actually form an enriched category. Okay, this enriched category, this B is the dream field center of rep G, which is precisely the category of bulk excitation in the 2 plus 1D finite gauge theory. And this A sub H omega is the Lagrangian algebra associated to a particular gapped boundary of the finite gauge theory. Okay, and this S is the category of topological excitation on the boundary. Okay, so the dictionary is the same. All right. Okay, so this is the one way you obtain by classifying all possible observables. You also obtain a classification of bosonic fermionic gapped quantum phases, including the symmetry breaking phase. Okay. Yeah, I will skip unless people ask. Okay, so we have seen that this enriched category can be realized as a topological skeleton of a gapless 1 plus 1D quantum liquid, right? We have shown this before, but the question is, can this enriched category define the topological skeleton of a gapped 1 plus 1D phase? The answer is yes. Okay, this can be realized the topological skeleton of 1 plus 1D gapped quantum liquid. There are many work, concrete work of construction of a lattice model to show this works. You can view it as simply as equipped with algebra higher symmetry or fusion category symmetries of this gapped quantum liquid phase. Okay. All right. I want to at the end of this section, I want to emphasize that these duality have been obtained explicitly or implicitly discovered by many group of peoples in a different contexts. Okay, maybe the early one I can find is the Fritz Telemann. Okay, and many different contexts. So I won't go through them for the limit of time. But I want to point out the story I told in this section mainly follow the three work highlighted in the blue color. All right, so let me take a look at the time. How long do I have? Okay, so let's move on to ND case. Okay, ND case. Let me first state the ND results. Using a very independent argument, we sort of prove a physical proof of the following holographic dualities. So an n plus 1D topological order plus a gapped boundary is a holographic dual to ND gapped quantum liquid. Okay, and which is more completely defined by a topological Wick rotation, as I described before. So this topological Wick rotation simply changes this pair. One of them is the category of topological order, category of topological defect in the bulk, and the other is the category of topological defect on the boundary to an enriched higher category. Okay, so let me give you a outline of the logic flow behind this construction. Do I have time? Yeah, let me quickly go through this. So consider a 2D SPT order with an onset symmetry defined by a finite group G. In this case, the category of G charge is simply a rep G. Okay, it seems that there's no further particle like a macroscopic observable in such SPT orders. If a 3D SPT just described a rep G, then it becomes confusing because it contradicts to the well-known three-cycle classification of the 3D SPT phase. So clearly there are some data is missing. Okay, the way out is using idea of gauging. Okay, there are two ways to do the gauging. One is introduce invertible domain wall or twist defect. This leads to the G cross the Brady diffusion category. Another is by adding additional topological anyons, which also called gauge flux. This leads to a modular sensor category minimally extending the rep G. Okay, the way of this leads to the so-called minimal modular extension of rep G, and both gauging are not unique, so they recovered. So the gauge idea is successful in that it recovered the classification. Okay, so this is not trivial result. However, it does not give an intrinsic description of SPT order because SPT order should have a well-defined mathematical description before we gauge it, right? So here comes another idea from boundary bulk relation, which says that well, since G charge are symmetric and cannot detect each other via the double braiding, so according to the remote detector principle, the topological phase should be able to detect itself using double braiding. So in some sense, this rep G should be viewed as in some sense anomalous, because they cannot detect themselves. They're completely symmetric. Okay, according to the boundary bulk relation, it's the anomaly have to be or maybe anomaly inflow. The anomaly inflow principle. This anomaly have to be cancelled. Can be cancelled in its 3+1D, a fictional bulk. Okay, so I draw a fictional bulk here. Which is given by its Drinfeld center, okay, of the G. I secretly change. So in general, there are I secretly change the rep G to 2 rep G, okay, because I need to include a certain condensation descendant of G charge. Let me not spend too much time on this. Just take it for granted. Okay, then its Drinfeld center is the Drinfeld center of the 2 rep G that describe the 3+1D bulk. Which is a trivial SPT, 3+1D, trivial SPT. Okay, it turned out that there are multiple ways to identify the 3+1D bulk by itself, with itself, via the so-called Brady autoequivalence, which can also be viewed as invertible. All these Brady equivalents can be viewed as invertible domain wall, Wi-Fi. So what is Wi-Fi? Wi-Fi is an invertible domain wall between trivial 3+1D SPT phase and the trivial 3+1D SPT phase. So this become invertible 2+1D phase itself. So Wi-Fi is precisely a 2+1D SPT. Okay, so indeed, so you can check mathematically, this Brady the autoequivalent, the set form a group, and this group is precisely the cohomology group. Okay, this recover the classification. Okay. For the time reason, maybe I'll so this leads to us a classification results. So maybe let me state it. And SPD SET order with a higher symmetry, let me restrict to R to be nrep G or nrep GZ. And it's completely characterized by a fusion category A with a Brady embedding. And satisfy certain conditions, and this condition can be. Let me not go through the through detail. I will explain. Maybe I will explain the result using one example. Okay, the 2+1D example. Even though we're working with 2+1D or n+1D, but the example still easy to explain in 1+1D. Okay, the higher dimension is the same, but I think it's more illustrative to do 1+1D. In the 1+1D gap the liquids, assuming there is an internal Z2 symmetries, and this picture, okay, this picture is reduced to this picture. Okay, so on the one side, you have a one-dimensional higher. In this case, it's exactly 2+1D toric code, and it have 2 gap the boundaries. Okay, one is rep Z2, another is vac Z2. Okay, then you have a gap domain wall. You have a invertible domain wall which is given by EM duality. Okay. There's also fermionic part for the limits of time. Let me just focus on this one. So what is it? The important thing is that the rep Z2 in the previous setting, the rep Z2 is our symmetry, is a symmetry charge, and the E particle is the symmetry charge. Okay, but in the but when you in this bosonic case, okay, let's not consider the fermionic case. So the EM duality breaks the Z2 symmetry. Why? Because E is the symmetry charge, but this duality changed E to M. M is not symmetry charge anymore. Okay, so as a consequence, this duality change the break the symmetry. As a consequence, the Ising chain has a trivial SPT, which is given by this pair, trivial SPT, and another is the symmetry breaking order. You can obtain from using this pair, or maybe well, more precisely using this autoequivalence. This autoequivalence, EM duality, break the Z2 symmetry. So it's a symmetry breaking order. Okay. There's a similar story in the fermionic part, but let me skip it. All right. So this classification can be generalized because previously our R, the symmetry R in our theorem, is just restricted to this two case. You can generalize it to any fusion n category, n minus one category, as algebra higher symmetry. Then we obtain the characterization of ND quantum liquid by n plus 1D topological order together with a gapped boundary. Okay. However, this is still not an intrinsic description of ND gapped quantum liquid. Why? Because in the lattice model realization, the n plus 1D bulk is not there. It's completely empty. So we're still one step away from the final characterization, even though this characterization works. Okay, so the last idea need to complete the story is topological Wick rotation. You simply rotate these data. Remember this data, which characterize one-dimensional lower quantum liquid by our previous analyze, actually can turn into a intrinsic mathematical description of the top of this ND quantum liquid by using enriched category. Simply rotate this pair to time direction. By that I mean replace this pair by an enriched category. Okay. All right. So basically, what does this mean is that if you have a previous picture, right, of this picture, after topological Wick rotation, simply produce this enriched category. This enrichment can be traced by this autoequivalence. Okay. For this picture is same. Remember this picture is describing a 1 plus 1D phase. Okay, but this is not intrinsic because it involved 2 plus 1D bulk. But after you do the topological Wick rotation, you obtain a 2 enriched category, and this description, mathematical description, is intrinsic. Okay, every observable associated to this data is living in the space time of the lower dimensional phase. Okay, this is for fermion. I didn't talk about that. All right. Okay, so I described the general theory. This is a model-independent argument. You might wonder, are there any more physical example using lattice model? Yes, indeed. If you restrict to S to this case, there are many work about a lattice model, explicit demonstration where a lattice model, and more is coming. But for generic S, I think the lattice model construction is still not there, but you can use the following idea of a lattice model proof. You simply recrotating a n plus 1D 11 model based on the fusion n category, plus a gapped boundary condition defined by a module category, and you rotate it to n plus 1D spacetime. What's the meaning of that would be maybe will be clarified in the future, not here, but that's just an idea. This idea have been implemented in 1 plus 1D actually. So, okay. Anyway, So now I want to, we have discussed the holographic duality of ND case, but I want to tell you that holographic, this topological weak rotation automatically give you a generalization. You consider a gap domain wall between two n plus 1D topological order. Okay, S is a gap domain wall. Now you rotate it to a time direction. You simply obtain this picture, and this picture is simply this is a ND is ND topological order, but with a potentially gapless boundary of C. Okay, so this is a generalization of traditional holographic dualities. Okay, and the interesting thing is that this enriched higher category, if you compute the Drinfield center, you got a bulk. So the bulk boundary relation always hold. Okay, bulk is the center of the boundary. So this is one of the generalization. All right, so I already finished to describe the holographic duality of. Yes.
I think conceptually, I still feel this weak rotation is a bit weird.
Yeah, it's really weird. I agree. But I'm trying to clarify now. Okay, why I use the topological weak rotation.
What I mean is that you are trying to say originally topological order is in the spatial slice, and then partly time slice. But topological order usually it's not just a space slice; it's already also in the time evolution, unless you try to eliminate the whole system, right?
Yeah, I agree with you. It sounds unphysical. But it's at first we introduced this. So the first paper we wrote, we use this trick all the time to do our computation because we feel it's powerful, but we don't know the physical meaning, so we didn't give a name until 2 years later. We find it's really this is not only powerful, it has a lot of applications. So that's what I'm going to talk about now.
Okay, go on. Thanks.
Okay. Yeah, so why we call it the rotation, you might wonder. So it's just, instead of just a holographic duality as everybody else was doing. Well, because the rotation suggests that all the geometric intuition are preserved like a real rotation. Okay, so the holographic dictionary automatically extends to a higher codimensional domain wall on both sides. Moreover, this holographic map or dictionary is compatible with the fusion of domain wall. What does this mean? This means holographic duality is actually functorial. Let me explain this using a picture. So this picture can be viewed in two ways. Before the topological weak rotation, the vertical direction is nth dimensional space, nth dimensional space direction. Okay, now you got a pair. One is the bulk and one is the boundary. But after topological weak rotation, you can view the vertical direction as time direction. Then this pair become enriched category. Okay, the interesting thing is that this pair can have domain wall, right? In the bulk, you can have a domain wall. On the boundary, you can also have a domain wall. Okay, so on and so forth. Okay, the interesting thing is that after you do the rotation, the domain wall, which is defined by a pair, also become an enriched category. That become a enriched category, which a domain wall on the lower dimensional side. Okay. Moreover, the this holographic dictionary is compatible with fusion. That means you can on the higher dimensional side, you can fuse this domain wall. Altogether, you also fuse the domain wall on the boundary. That's equivalent to you first rotated to time direction. Okay, do the topological weak rotation, then do the fusion. So I want to say, right now, as Juan criticized, I still don't have a physical meaning of the topological weak rotation. We just find it very convenient to catch all this geometric intuition. Okay. Moreover, I want to point out that the holographic dictionary automatically include the dictionary map of the duality because many of the duality can be realized by invertible domain wall. Invertible domain wall in the one-dimensional higher theory. After topological weak rotation, become invertible domain wall in the lower dimensional theory. Okay, for example, the EM duality is mapped to the Kramer-Wiener duality. EM duality of toric is mapped to the Kramer-Wiener duality of Ising J. Okay, Another thing you can do with the topological Wick rotation is that is also give a description of a gapless boundary. Look this this black line labeled by M is actually a gap domain wall between three faces, C, D, A. Okay, but I rotate A to the vertical direction, to the time direction, simply represent these pair. These pair represent a gapless domain wall between the C face and the D face. And similarly, this is another gapless domain wall. Even though we don't know the precise fit, well, we know the we know some we know mathematical meaning of this, but we don't know what the physical deep reason behind it. But it provides a very powerful computation tool. If you want to compute the fusion of this two domain wall, you can simply fuse naively. You fuse them along the topological defect line, right? The topological order, higher dimension topological order. Then how you do it? You just fuse them component-wise. This chiral symmetry or non-chiral symmetry is fused as a tensor product over vector space. And M is fused with N along the D, okay? And the A and B, because in the between A and B, there's nothing, it's trivial. So simply stacking this to, you got the Lattice tensor product. This is give a correct formula for fusion to gap the domain wall. In particular, if you, for example, if you have a gapless edge of a 2D topological order, and this edge can be viewed as a domain wall between the non-trivial phase and the trivial phase, then you can fuse this edge by squeezing this solid cylinder. This is time direction, okay? You squeeze the solid cylinder, you become you obtain a 1+1D phase. As a consequence, previously when people argue this dimension reduction, they use a physical argument to show what the result could be. But here you simply compute it because we have all the theory. The theory give you all the computational tool. You just compute the simple formula of the fusion domain wall, and you recover every. In this way, you can recover every modular invariant 1+1D rational CFT. We know so far, yeah. Every one of them can be reproduced in this process by using this simple formula. So what I'm saying is that this is pretty powerful, very powerful machinery. Okay, let's see how long. I started 5 minutes late. Can I go on for 5 more minutes?
Yeah, take your time.
Okay, so yeah, this is one of the power of yeah. Let me skip this unless people ask. Now I want to consider further generation. You see, this dictionary is pretty strange. You start with the n+1D topological order with a gapped boundary. You might ask, why gapped boundary? Can I change gap to gapless? Or can I change the boundary to maybe some other defect of higher codimension? Yes, indeed. Let me give you this. So you can change the gap boundary to gapless boundary. It's explained in the following situation. Consider two topological order C and B and a gap domain wall S between them. Okay, S is a gap domain wall between C and B. Now you do a folding trick. Then S become a gapped boundary of a double layered topological order. Okay, then you do a topological Wick rotation, you obtain a one-dimensional lower quantum liquid. Okay, you got an enriched category. Okay, on the other hand, you can do in a different way. You can first rotate B to the time direction, do the topological Wick rotation. You obtain a gapless boundary of C. Okay, then you rotate C to the time direction. Okay, you obtain a new holographic duality. In this case, the boundary become gapless. So what this example to show you that, well, there's nothing special about the gapped boundary. It's just convenient choice for us to study our discussion. That's all. It's convenient choice, not the fundamental required. Now, what about the other? You start with the boundary. What about the using some other defect or higher dimension? Yes, indeed, you can consider following situation. You consider n special dimension. You can consider a bulk topological order with two boundary and with a corner. Okay, corner is a higher codimensional domain wall. Okay, you rotate it to the time direction. What do you got? You got a quantum liquid of a lower dimension and with a gap with a potentially gapless boundary. Okay, you can also look at this picture. This is time direction. Okay, now you do something crazy now. I don't even know what, physically what that means. Okay, but rotating and plus fusion. So you look at this shaded area. You fuse A with C. Okay, you fuse A with C along this Z1A. Okay, you obtain even lower dimensional quantum liquid. Well, you probably want to, the last process which involve a fusion, well, so right now we don't even know what the meaning of it, of this fusion, right? But this fusion is well defined on this stage, right? Because every here in the spatial dimension, you can define the fusion. But this become ambiguous. But let me just take the intuition, geometric intuition. So this involves fusion. In general, it's not one-to-one.
And it's increasing in the radial variable.
What? Excuse me? Oh, did I hear? Oh, okay. Let me continue. Maybe it's just some noise. So this is involve fusion. So in general, it's not one-to-one map. So it does not give us duality in the Euro sense. However, this problem can be easily fixed by adding additional data. For example, you can say ND quantum liquid. If you specify an algebra higher symmetry or fusion category symmetry A plus a boundary, then you can show this is a holographic dual to N-1D quantum liquid with a categorical symmetry over A. What do I mean by that? Is a categorical symmetry over A is mean a monoidal functor from A to the center of E0 center of S. Let me ignore the detail. It can be formulated. So what I'm trying to say is that it's nothing special about the boundary. You can even generalize it. Well, you can even further generalize the procedure to even higher codimension defect if you want. Okay. All right. So I only have 1 or 2 minutes. So let me finish. So we have seen a holographic duality based on the topological Wick rotation, and this picture is perhaps a crucial ingredient of a unified mathematical theory of both gap and the gapless phase. We hope that this talk can convince the reader that topological Wick rotation can provide some new insight other than the Euro holographic duality, and more applications of this rotation are yet to come. Okay, and one of our aim behind all this study is yet unknown mathematical theory of higher dimensional conformal field theory. We hope that we can tell you more about it in the future. At the last, I want to give you a short discussion of the relation to ADS-CFT dualities. So we intend to propose that we should regard ADS-CFT duality and the topological holographic duality discussed in this talk as part of a unified framework. However, our discussion of their analogy is so far is limited to only 2 features. One is gauge symmetry is mapped to global symmetry. Another is one-dimensional higher side require not only the bulk, but specify the boundary condition. Okay. Well, the reason for this limitation is that topological defects are missing from ADS-CFT dictionary. I put a question mark there because I don't know much about the literature in ADS-CFT. I'm pretty sure there is some work about the topological defect, but I guess, maybe they're not complete enough to address the category of topological defect on the ADS side and do a topological Wick rotation to obtain topological skeleton of the CFT side. But we don't know, yeah. But that's just a question or conjecture. And another, on the other hand, the local quantum symmetry or the information of a local observable algebra, which is needed to recover the correlation function, are completely missing from the topological holographic dictionary so far, right? So let me address this a little bit. So ADS-CFT dictionary, in a very special case, in the so-called topological trace sector, Costello and Li Si, Kevin Costello and Si Li, formulate this dictionary on local observable algebra as a Cajou duality. Okay, it turned out that topological holographic dictionary if you restrict to local observable algebra, for example, in the 3D quantum double model or level 1 model, you got a Hopf type of LOA. But on the CFT side, you got a E2 algebra. VOA or full field algebra can all be considered the conformal analytic analog of E2 algebra. And the general spirit in the community, people agree that these two are Cajou dual. Okay, even though I don't know anyone write down the detail. However, if you don't use this language, you can replace the E2 algebra by conformal net of local observables. That's also a successful framework to study rational CFT, and you generalize it to a topological net, some generalization of conformal net, and it turned out that you can obtain this generalization of topological net from level 1 model. Okay, you can. So that what I mean is that previously I started the talk by giving you holographic duality only using topological data. Okay, topological pair of data mapped to an enriched category. Now what I'm saying is that this can be generalized to other data as well, including the local quantum symmetry. So this will be more complete. Okay. At last, I want to point out there's some information I got only yesterday. So ADSF dictionary. It says that n+1d spatial dimension in the ADS set is dimension of RG flow in the CFT side. Okay, an interesting work by Hong, Janet Hong, and she told me that in a recent work they can show that recursive application of RG step just means cross graining in the box theory would result in a collection of tetrahedra that describe discretized Euclidean ADS space. In their study of constructing d-dimensional CFT from d plus dimensional TQFT. So I think this is a very interesting development. Yeah. So the last one, I will end my talk by a question to the audience. Are there any more evidence? Maybe the audience know. I will stop my talk here. Thank you very much.
Thank you very much. Thank you, Liang.
Thank you.
Thank you. So, any comments from the audience? I have one thing to say about the maybe 2 slides back about the relation between CFT to ADS. You try to relate the topological defects of ADS and maybe topological skeleton on CFT. One thing about if there are some topological defect in the quantum gravity theory on the left-hand side, I think it implies there is some global symmetry actually, because the modern notion of the symmetry is identified as topological defects. But if the global symmetry is absent in the quantum gravity theory, as we believe, then those topological defects will also vanish in some way. They should be trivialized. It's related to the trivialization of a cobordism class, the cobordism or this cobordism hypothesis or cobordism conjecture. Sorry, maybe on the Swan community. So there should be additional kind of constraint, even if you find topological defect from the ADS side. That should be trivialized in some way.
I see.
But on the other hand, I think there are people in the recent development on people study relations of the so-called symmetry TFT of using string theory and try to also identify some kind of a topological defect in the string theory. So I feel like these 2 things somehow has some tension, and
I see.
I don't know which side of the coin I'm looking at. Either the topological defect should be gone, but on the other hand, it's also useful to find topological defect. I'm slightly confused on the best way to describe that, but I just.
So you're saying that the gravity theory should not have a global symmetry. This should generalize to even higher non-invertible symmetries.
Every possible symmetry, I think.
I see.
And that's the symmetry is measured by the topological defect or operator that link with uncharged objects. So the topological defect is the symmetry generated.
So the question will become: are there any topological defect on the CFT side?
I suppose yes. With global symmetry, yes, you can have.
I see.
Okay. I don't know enough about what does this imply. But people do try to find topological defect also in string theory, and I think maybe these are not, there's no conflict, but just a point of view.
Yeah. So may I ask for a topological defect in string theory? If you view string theory particularly as a conformal field theory, it's very natural to consider topological defect in conformal field theory, right?
Yes, but if you consider left hand side as a full quantum gravity theory, that's what I say. Then
Yeah.
the topological defect that should be trivialized in some way.
I see.
But yeah.
Yeah, that's interesting. I'm also got confused about that. Yeah, I don't know.
Yeah, these are called the cobordism or the cobordism conjecture, I think.
I see.
Or, yeah,
So it suggests that one should be cautious to relate this to, right? Yeah. Okay. Yeah, that's okay for me.
there should be some additional clarification on this relation.
Right. I agree. It's a lot of things. This kind of question is still is still mysterious. I talked to expert in the higher energy community. The feedback I got is a mixture of optimistic or pessimistic point of view. They're both point of view are common. You know, some people think this is reasonable. Some people think, well, you know, it's hard to get this gravity part out of this consideration of topological phases. Yeah, I kind of I don't know. I think yeah, we probably have to wait and see. Especially we are in a stage, in an age that a lot of new results is coming, maybe day by day. So many results, it's hard to tell.
So, any other questions, comments from the audience?
May I ask a question about this local quantum symmetries? Actually, I don't know much about these local quantum symmetries. Roughly, what exactly are they?
Roughly, you can be viewed as a local observable algebras. If you're in a high energy community, you probably, or so if in CFT it just means VOA or is non-chiral analog. In a conformal net setting, it will be a net of local operator algebras. But this net of local operator algebras can be easily generalized to higher dimension. We introduced the concept of topological net of local operator algebras. These are mathematical structures we refer to when we talk about the local quantum symmetry.
I see. Then, in this context, in your paper with Zhenghao, does that mean that you can does that mean that there is an explicit linear map between operators on the topological model and the and conformal primary on the CFT? As in, does that lead to a prescription of something that I do on the topological, on the Levin-Wan model, and that would correspond to inserting a conformal primary in the CFT? Is that the right way to understand this duality?
I tend, even though I don't use this language, but I tend to say yes. I mean, in the level one model, you can see all the topological defect, and this topological defect after this holographic dictionary is mapped to topological defect in the CFT. But the topological defect in the CFT are also labeled by primaries. So I cannot say they're. I should say yes. I would say, but
okay.
Yeah, but maybe more so. But on the worksheet, I prefer to say topological defect line instead of primary. But they are primaries, yeah. So MAA, the field living in MAA are primary field and their descendant.
I see.
Yeah. The physicists prefer to use that primary language, yeah, right, yeah. But I would say yes.
Okay, I see. Thank you.
Any more comment question? Okay, so I think we should thank Liang Kong again. Thank you very much for your time.
Thank you for organizing this, hosting this.